Welcome to Genetic 7, Predicting Genetic Change from Selection. So, as an animal breeder, we're going to select top animals, and then we need to predict how much genetic change do we expect for the next generation. So here's our equation for predicting genetic change, delta G. Delta is the symbol for change. G is the symbol for genetics. So the change in genetics equals the heritability for the particular trait times our average selection differential. So the average selection differential is going to be the superiority of our parents as a deviation from their pen mates or herd average. So let's go through an example. So in our example, we're looking at beef cattle. A beef cattle producer wants to select for increased yearling weight. Current adjusted average is 1,050 pounds. So selected bulls for the next generation average 1,100, so they're plus 50. And we're saving most of the heifers back. We've only got a selection differential of plus 10 pounds on them compared to the herd average. And we know that the heritability for yearling weight is 0.3 or 30%. Now, when we're talking about adjusted average here of 1,050 pounds, we've got an adjusted average for the bulls and the heifers. The adjusted means that we have adjusted for gender differences. Obviously, bulls grow faster than heifers, but we've made the adjustment, so we're gender neutral. Older cows tend to raise bigger calves than younger cows, so we've adjusted for age of dam. So we've made some adjustments to try to keep everything somewhat on an equal basis. So we can now plug our data into our formula. So change in genetics equals the heritability, which is 0.3, times the average selection differential. The bulls were plus 50, the cows were plus 10. So our average there is 30. That's the average selection differential, 30 pounds. Times 0.3 is 9 pounds. So from one generation to the next, we're expected to make 9 pounds improvement. So how much should those yearlings weigh next year? Well, the previous year we were at 1,050 plus the 9 pound genetic change. All other things being equal, we're going to expect that next year our animals at a year of age should weigh 1,059 pounds. But wait a minute. Our bulls, the parents, averaged 1,100 pounds on the male side. Our cows average 1,060. If we look at the average of our parents, they actually averaged weighing 1,080. Yeah, we're only 1,059. Shouldn't our offspring be the average of the parents? Well, that's true if the heritability is 100%. But the heritability in this case is not 100%, it's only 30%. So these bulls were plus 50, but that's not all due to genetics. 70% of that deviation is due to environment. Our top animals were ranked on top because for Part of that is because they had a better environment on average. And our cows had a better environment than average. Those better environments are not going to be transmitted to the offspring. Only the superior genetics is transmitted, and only half of that is transmitted. So that's why we're dividing this by 2 here. So again, as far as predicting genetics change up here, it's the heritability, and that's only 30% in this case, times the average selection differential. So our genetic change was plus 9 pounds. So it's a genetic change is always a little slower, but after we do this for several generations, we're going to make progress, and significant progress. 9 pounds per generation. Do that for 10 generations, and that's 90 pounds. And the whole moral of the story is, as far as genetic selection goes, you need to be patient. But it accumulates generation after generation. These 2 horses have the same ancestors if we go back 700-800 years. So the horse on the left, ancestors have been selected for increased size, while the horse on the right, the ancestors were probably selected for smaller size. So after many generations, we can make a lot of progress. So we've got some review problems here for you to work on. And that's going to be through the rest of this video then. So here we got a qualitative trait, polled versus horned. The polled gene is dominant over the horned gene. Mated herd of cows where the frequency of the polled gene is 0.2. What percent of the offspring would be expected to be polled? Well, for this, I think we need to set up a Punnett square. So we've got the Punnett square set up, and we've put the alleles from the male here and down in this column, and then we carry through the genes from the female. Now we do need just to do some multiplication. 0.2 times 0.5 equals 0.1 in this square. So we've multiplied through here, and we'll find that these squares are going to be the polled animals. So 60% of the animals are going to be polled. And 40% of the animals would be expected to be horned. Okay, another review problem here, and I think we're going to have to use the Hardy-Weinberg equation for this particular problem. We've got 1 out of 400 animals born with a recessive genetic defect. So it's recessive, so we need 2 copies of that defective gene for it to show up. And frequency of this equals 1 out of 400, which is equal to, I guess, 0.0025. So we got to change that fraction into decimal notation. What's the frequency of the gene? Well, that's going to be the square root of this, and the frequency of carriers, that's going to be 2pq, right? So we've got it set up here. We've got the Hardy-Weinberg equation on top. So here's our Hardy-Weinberg equation. P squared, 2pq, q squared equals 1. We know what q squared is. That's the 0.0025. So now we can solve for q and solve for 2pq. So Q is the square root of the 0.0025, which is 0.05 or 5%. The frequency of this defective gene in our population is 5%, even though only 1 out of 400 animals show the recessive genetic defect. Frequency of carriers is going to be 2pq, and that is 0.095 or 9.5% of the individuals in our population are known to be carriers. In our final review problem here is on predicting genetic change. So we're selecting for leaner pigs. So the boars average 0.2 of an inch leaner per back fat. The gilts are 0.1 inch leaner than average. So this is our breeding stock. We're selecting for leaner pigs. Average back fat currently is 1.1 inches at 280 pounds. So we want to get just a little bit leaner pigs. Now, nice thing here is heritability is relatively large at 40%. What's the expected fat thickness of the next generation? Well, they should be less than 1.1 inch, but how much less? Well, here's the formula for change in genetics from one generation of selection. So it's the change in G is the heritability times the average selection differential. And our selection differentials was minus 0.2 for the boars, minus 0.1 for the gilts. So we just need to plug this in to the equation. So here we go. How much genetic change? Heritability is 0.4. Here we have the average selection differential. So our pigs will be minus 0.06 inches leaner than the previous generation. So they were at 1.1 minus the 0.06 will give us pigs that are 1.04 inches of back fat in the next generation. So this includes this little video on calculating or predicting genetic change.